Space, the final frontier. It seems dark and empty, yet it harbors some of humanity's best hopes for expansion. And asteroid mining seems to be the next one. Asteroids hold a wealth of resources just waiting to be extracted. But sending a spacecraft to one of these asteroids is like trying to hit a 100-mile-per-hour baseball with a dart from a mile away. In other words, really, really difficult. Yet, that doesn't stop many companies today from trying to achieve the seemingly impossible. With both physical and chemical methods, private companies are trying to mine asteroids for their valuable resources. One simple method is extracting samples of the asteroid by drilling it and then returning the materials to Earth. Once on Earth, it can be processed and refined for use. Most asteroids contain large amounts of water, a vital resource for space travel. One method for extracting water heats solid samples of the asteroid to boil the water out for distilling. Finally, small, self-replicating robots could be used. They can travel to the asteroid and harvest its useful elements. While asteroids are huge, these small robots using the material from the asteroids could replicate exponentially, chewing up asteroids in a reasonable amount of time. From water to iridium, asteroids are full of useful materials to aid in the future of space travel. These incentives could spark an asteroid mining industry which would greatly boost Earth's global economy. In fact, NASA estimates that the materials just in the asteroid belt could value up to $100 billion for every person on Earth. Gold, silver, and silicon found on asteroids would help the electronics industry, while rhenium could be used to advance the search for the cure for cancer. Iridium, found on asteroids, could be used to create antimatter, causing an explosion in scientific research, eventually leading to the creation of faster-than-light travel and maybe even laser swords. Or it could just be really cool. Either way, asteroids have the potential of changing the course of humanity forever if we can figure out how to get to them. Asteroids exist in a rather nebulous legal region, so the future of asteroid mining might exist less in space and more in the courtrooms. Beyond legal complications, asteroid mining is currently expensive due to our inefficient methods of space transportation. Despite these challenges, we continue to develop technology to achieve the impossible. Who knows? Maybe in a couple of decades, the final frontier won't look so empty after all. It is no secret that electricity runs our lives in the 21st century. Electricity is caused by electromagnetism, which is one of the 4 fundamental forces that govern our universe. But why do these forces exist, and where do they come from? The Standard Model was an attempt by scientists to decipher the underlying mechanisms behind these forces. Quarks, leptons, and gauge bosons are all particles that make these interactions possible. However, there was a glaring hole in the Standard Model. It proposed that these particles should have no mass, but this is at odds with experimental evidence. Attempts to account for this discrepancy led to the premise of a Higgs field, an explanation for how these elementary particles have mass. It was the discovery of the Higgs field that completed the Standard Model. How does the Higgs field give particles mass? For example, an electron has the mass of 1 billionth of an elephant, while a photon, another elementary particle even smaller than the electron, has no mass at all. The electron, hampered by its mass, can only move at a fraction of the speed of light. Photons, without mass, are free to zip along at light speed, or nearly 300 million meters per second. So why are electrons and other elementary particles bogged down with mass while the photon is free from such restrictions? The answer lies in the Higgs field, a field that encompasses the entire known universe with energy. To us, the vacuum of space looks empty and desolate, but to a subatomic particle, it is as hectic as a crowded party. When a lonely photon enters the party, its relative obscurity allows it to pass through unnoticed, enabling it to move through the crowd with ease. On the other hand, the electron is the life of the party, and gets stopped by others constantly, so it must slowly trudge through the crowd. In this metaphor, the Higgs field is the party, and a particle's popularity is its interaction with the Higgs field. But this constant interaction with the Higgs field forces the electron to travel much slower than the photon, giving the particle the appearance of mass as it is not traveling at the speed of light. Although this makes sense from a theoretical standpoint, this universal party, the Higgs field, is unobservable with our current technology. This raises the question, how do we know the Higgs field exists? Typically, subatomic particles are found through high-impact collisions and particle accelerators. To prove the existence of the Higgs boson, they would need a particle accelerator larger than any one before it. This became the Large Hadron Collider, located in Switzerland. The byproducts of these collisions would only rarely include the particle. But by 2012, they had caused enough collisions to confidently affirm the existence of the Higgs boson. With the discovery of the Higgs, the Standard Model was finally complete. Beyond the Standard Model, scientists anticipate that the Higgs boson could be a gateway to even further understanding of the fundamental nature of the universe and a true theory of everything.